Four Colors Theorem by me. If you have or create a map or plane with divided sections, the Four Colors Theorem states you should be able to color the sections with four colors in a way that no two sections with the same color share a common side. So let's get started. In this video, I'm going to show you many ways to prove the Four Colors Theorem. One of them I have right here. I've taken a regular sheet of paper and made it into a map or plane by dividing it into sections. And then I colored it in using only four colors by using the Four Colors Theorem, meaning that no two of the same color can touch at a common edge. So, like this green and green, they touch at a common vertices but not a common edge, so it works and it looks organized. But, for example, if you use a bunch of rainbow colors to color it, it might not look as organized and it might kind of get confusing. Now I'm going to prove to you that the Four Colors Theorem works by proving that the Three Colors Theorem doesn't work by using students at my own school. So at my school, I made two different groups. One of the groups was wearing four different colors and the other group was wearing three different colors. I made two planes on the ground with different sections. Each student had to stand in the section, and they had to organize themselves so that if a person of the same color was standing in the section next to them and that section shared a common edge with them, it wouldn't work out. The Four Colors Theorem people, which is on the right, did it pretty easily. The Three Colors Theorem people, which were on the left, had a little bit of trouble. This picture was taken after all the students had thought they had found their correct placement. I put a dot over their head that shows the color of the t-shirt that they were wearing to make it a little bit more clear. As you can see, the Three Colors Theorem people did not do it correctly. They're on the left. They had a blue and a blue connected. A line between the two means that they are connected by a common edge. So as you can see in the corner, there is a blue and a blue that are connected. But if you look at the Four Colors Theorem people, they don't have any of the same two colors connected by a common black line, which means that they aren't connected by an edge, which means they did it correctly. So what I'm trying to prove here is the Three Colors Theorem did not work, but the Four Colors Theorem did. A famous man called Augustus de Morgan showed us that if we make a plane and divide it into four sections, that each section can have its own color and that the two colors won't touch at a common side. But for example, if we consider the outside region, like if we took this as the outside region and put the plane in the middle, then it might not work because considering this, the black is touching the black there. So we might have to put it in the middle, the black in the middle. Now, Euler's formula, which was adapted by Augustin Cauchy for two-dimensional figures, takes a three-dimensional figure and basically squashes it down, and so we have five sides, which I will show you in the next video. Euler's theory basically states that f plus v minus e equals 1, which might sound really confusing, but really all it means is faces plus vertices minus edges equals 1. Now, if we wanted to consider the outside region of the net, like we did for this one, the outside, we would have to do the same formula, but instead of adding 1, we would have to add 2. So here's what it would look like if we squashed down a cube and made it into a two-dimensional figure. And we would have to use that formula, which is f plus v minus e equals 1. But if we, for example, consider the outside region, which I will shade in here to show you, we would have to do the same formula, f plus v minus e equals 1. But instead of the 1, we need to change it to a 2. So f plus v minus e equals 2. After further looking into the equation, the men figured out that really, by counting the number of edges, vertices, and faces, that when they plugged those numbers into the equation, it didn't work, and it came out to be 0 when it should have came out to be 2. Another method that was used to try to solve the Four Colors theory comes from Alfred Kemp, and that's called Kemp chains. Before we go into that though, I'm going to explain what a planar graph is. It is a graph drawn in a plane with no edge crossings, like the one in the picture. The first thing Kemp did was consider graphs with triangles as the face. He did this because triangles are the shape with the least amount of edges. And now I'm going to explain to you what a maximal planar graph is. A maximal planar graph is a planar graph that includes the most amount of edges possible. Any maximal planar graph must include at least one node with a degree 5 or less. A node is a point in a diagram where the pathways intersect. A degree of a node is the number of edges it's connected to. In your graph, you need to indicate the number of edges, faces, and nodes. Then we plug in those numbers like we did earlier with Euler's formula. Each face of a maximal planar graph is bounded to 3 edges, and each edge is the boundary of 2 faces, so we have f equals 2e divided by 3. Some important formulas in Kemp's methods were Euler's formula for a complete planar graph, the sum of degrees of all nodes, and the average degree per node. So thank you for watching my video about the Four Colors theory. I hope you enjoyed it!